Good afternoon, everyone. This is Ahmed Fayed of Group9, and today my colleagues Ahmed Aboutaleb, Ahmed Abouzaid, Dina U Ismail, Iman M Yehia, Youssef A and I will be presenting you our thesis project on medical Q&A system, supervised by Dr. Ahmed Rafea, Dr. Nouri Sakr, and Engineer Nada Ayman. Please have 10 seconds to look at the agenda of what we'll be talking about in this presentation. So giving you a fresh reminder on what a Q&A system is, it's a discipline within the fields of information retrieval and natural language processing, which is concerned with building systems that automatically answer questions posed by humans in natural language. It may construct its answers by querying a structured database of knowledge or information and can pull answers from an unstructured collection of natural language documents. Examples of that include a local collection of reference texts or a set of Wikipedia pages. Question answering systems have been promising since they present users with direct interactions through entering a query based on some facts or stories, and then the system tries to use the context in the supporting facts and stories to answer the questions. It answers them effectively instead of just giving out the best suited keywords. Besides, many problems in artificial intelligence and NLP can all be modeled as a question answering problems. For example, the task of text summarization can be modeled as a question answering task, in the sense that if the user asks the system what's the summarization of the text, it can answer the user by providing the appropriate summary. Our mission has been to design a system that can basically be used to utilize emerging NLP models to develop a meaningful Q&A system in the medical domain. This serves as a motivation to analyze research and improve all the solutions that have been proposed so far, including state-of-the-art models, BIO-BERT, and BI-LSTM. Our medical Q&A system aims to provide accurate answers to patients seeking answers regarding symptoms, and it can also provide definitions from medical inquiries. Therefore, it aims at solving two major problems, which are providing meaningful system for Q&A in the medical domain and improving the accuracy of previous models. So what we have done throughout this semester and what we plan on building on in Thesis 2 is that after submitting the literature review, the entire group took on the mission of exploring different NLP models and techniques. The literature review acted as our guide to knowing which models are worth investing more time in and trying to understand. And we found that BERT-based models and BI-LSTM models are the ones that give the best results. We have explored scholarly research that digs deeper into both architectures, going after the possibility of developing or building on the most appropriate hybrid model of both for the purpose of our research. And we were divided into 3 groups, doing 3 different experiments for that. After collecting data and analyzing results of the 3 experiments, we concluded with 2 experiments that are based on these models, and studied them intensively to propose our architecture to be further developed in Thesis 2. And now we move on to my colleague Dina Osama for further explanation on how we worked around the datasets that we had.
And now we will discuss some of the datasets that we utilized during our work. Starting off, one of the datasets that we used to fine-tune one of the models that we experimented with was the PubMed dataset. However, it was not used as it is. Sort of pre-processing of the data had to be done in order to ensure its compatibility with the model. So we first created a web crawler that crawled over the PubMed website in order to download all datasets at once. And then we created a parser that parsed these datasets, which were originally in XML format, and converted them to SQL-like database in order to be accepted by the model. This will be clear when we discuss the first experiment later on. Now, the second dataset that was used is the core duplicate questions dataset. Each point in this dataset is composed of a pair of questions where each pair has a common ID, and each question within the pair has its own unique ID. The last column as shown is a label that states whether the questions are duplicate or not. This dataset is used to train a similarity model that is a core part in the question answering system that will be discussed in a while in experiment number 2. Now we'll start talking about the experiments that we've done. Based on the literature review, the first experiment is about integrating BIO-BERT with BI-LSTM. BIO-BERT is a text representation technique that is also used to extract entities and relations, whereas BI-LSTM is responsible for the question answering part. The main purpose of this experiment was to prove the importance of training our architectures using biomedical data in order to yield better results. Further details about this experiment will be covered by my colleague Ahmed Rafea.
So the major feature of BIO-BERT that it is based on BERT, which is designed for training and label datasets with respect to the data context. As a result, the pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-the-art model for a wide range of tasks. Also, BERT has achieved 93.2 in F1 score, and one important difference between BERT and word-to-vec or other text representation techniques is considering the context of each token, which made it outperform the other techniques. And BIO-BERT is trained on PubMed and BMC datasets, which have more than 18 billion words combined, which give BIO-BERT advantage in the biomedical field, and that also explains having higher F1 accuracy and precision score than BERT in the name entity recognition and relation extraction. So after investigating the published BIO-BERT projects so far, we found that the product is providing the highest F1 score for the relation extraction by 2.8% and for the name entity recognition by 0.62%. However, the question answering and simulator lookup section provided lower score in the question answering evaluation, since it's based on FCNN or fully connected neural network. So for a dog product architecture, it contains a fine-tuned BIO-BERT for questions and answers to convert them into word embedding representation. The embedding is then utilized into fully connected convolutional neural network to develop an embedding which is used for similarity lookup. The top similar questions and answers are then used by GPT to generate an answer. So firstly, after retrieving the questions and answer batch and converting them into word embedding using WordBeast, while extracting the main entities using the name entity recognition layer and classifying the relation of the entities using relation extraction layer. The question and answer heads are being stored with their vector representation and their dot product values into the trained model. Meanwhile, the trained model is used to train the GPT model using each and every question and their vector representation, along with the dot product values to predict the most suitable answer for every question. And for the deployment section, the model received the question, then BIO-BERT converted into word embedding while performing the name entity recognition and relation extraction tasks. The question is redirected to its targeted entity section to create a matrix based on the question and answer similarities. Then, the answers are fetched and concatenated and then provided to the GPT model to select the most relevant answers. Finally, the user is able to select n number of answers based on their interests, and the order of these answers is based on the results of the normalized dot product matrix and the GPT model, which lies between 0 and 1 for the least to most relevant answers. So based on dot product evaluation, which has been done on 3 different datasets, which are NCBI, PubMed, and WebMD, it provided the following results in the name entity recognition evaluation: 89.05% in precision, 91.25% in recall, and 89.71% in F1 score. Also for relation extraction test results, it provided 79.21% for precision, 89.25% for recall, and 84% for F1 score. And finally, for the question answering evaluation, it provided 28.57% for accuracy, 47.7% for lenient accuracy, and 35.17% for MMR. And for the second project that we investigated, it's based on BERT for providing the embeddings and extracting the entities and relations, and based on BI-LSTM for similarity lookup and question answering. That's why the system is capable of answering combined questions which involve comparative and Boolean reasoning. And system scored 60% for precision, 66% for recall, and 63% in F1 score. So after fine-tuning the second project in our medical dataset, we've conducted a simple comparison to show the difference between the fine-tuned and the original model. The sample questions show that the fine-tuned model with PubMed dataset is capable of providing symptoms analysis and extracting the relations between 2 different entities as shown in the insomnia and bipolar disorder relation. And now Youssef will introduce the second experiment.
Now introducing the second experiment, which compares between 2 word embedding techniques, BERT and ELMO, as they are designed to take the contextual meaning of the word. These techniques are then followed by a BI-LSTM layer, and then finalized with an attention layer. As proposed in the paper titled An Online QA Healthcare Helper System, the researchers proposed a hybrid Q&A model in a chatbot framework. This model combines a knowledge graph to manage a medical database and a hierarchical BI-LSTM model to understand the question and fetch the answers from a large medical Q&A database. The figure on the right shows the hybrid Q&A model in the chatbot framework. At the top, the web interface interaction, which is basically the chatbot GUI, will receive the input question from the user and then send it to the system. That system will attempt to retrieve a reply using two information retrieval models. First, the information retrieval model will try to return the answer from the knowledge graph using the AUC algorithm. Second, if the appropriate answer cannot be found from the knowledge graph, the question will be moved to the question and answer pair module, in which they use a hierarchical BILSTM with an attention layer. This module is made to verify the semantic similarity between the user's question and the questions from the Q&A database. Finally, it returns the top k most related questions as the answer set. The knowledge sources used in the system can be divided into two. For the knowledge graph, they use the Neo4j graph database. This database is constructed by Health Navigator at New Zealand and contains more than 3,500 entities. For the Q&A module, they use the questions and answer pairs database of about 30,000 Q&As, gathered mainly from eHealth Forum, HealthTap, and WebMD. This model is designed to compare semantic similarity between two questions. It uses a BILSTM layer with an attention mechanism in order to detect the important keywords in a sentence. BILSTM itself is needed to capture both direction contexts. This system goes as follows. Firstly, the two questions are represented using word embeddings, especially word2vec. Secondly, the whole sentence embedding is captured by the BILSTM layer. After that, each BILSTM encoder output will be multiplied by a word attention value to highlight the keywords in the sentence. Finally, the similarity value is computed as follows. It's the weighted sum of the hidden state value multiplied by its attention value, and then returned as a confidence percentage. This percentage is then used to return the top k most similar questions. Now moving on to Iman to further explain the architecture of the experiment.
So moving on towards the HYPERPARAMETERS, the environment used to experiment the model is Google Colab to validate the semantic similarity between two sentences. For their training and testing, HPM was trained with a Cora duplicate question dataset. They further took a medical subset from their dataset where they had a dictionary for the symptoms and diseases. So from the dictionary, they collected almost 70,000 medical-related entries from the Cora dataset. Then for the training set, they randomly selected 10,000 entries to experiment with. For the parameters of HBM, they included the N epochs 9M, N hidden layer 100, the embedding dimension 300, batch size 1024, and max sequence length is 10. So moving on towards the evaluation. In order to evaluate the performance, they performed a comparison against BERT and BI-LSTM. They basically had 10,000 medical question pairs where they divided it into 6:2:2 for training, validation, and testing for BERT, while for the other two models, it was divided into 9:1. So it was clearly shown that the best performance among the three was HBM, as shown in front of us. Then they conducted another experiment where they took the remaining 50,000 medical entries. Also, it was clear that the three medical websites, HBM, performed the highest among the two other models. So, pros and cons for this model. So, firstly, I will start with the pros. Knowledge-based system provides target responses to well-defined questions. Therefore, it is more reliable to be used in a question-answering system. In knowledge-centric domains, such as medical fields, usually explanation of specific symptoms are sought and knowledge graph will provide the desired accurate result quickly. While for the con, in processing the input question with the questions and answers in the database, the hybrid model only computes the similarity between the questions of the user and the questions in the dataset. returning the most corresponding similar answer. However, the model does not do any further processing between the input and the question and the answer for further needed comparison. So moving on towards experiment 2 architecture, the main objective of our experiment was to enhance the accuracy of similarity model in the question answering system, as earlier discussed. In our base model, the training set consists of pairs of questions with a label that specifies whether they are duplicate or not. Each question in the pair is represented by word-to-vec embeddings, then passed to BI-LSTM plus attention layer. The similarity is determined by calculating the Manhattan distance between question 1 and question 2. Word2Vec provides a vector for each token or word, and those vectors encode the meaning of the word. The problem with Word2Vec is that a word has only one vector, but in real life each word has different meaning depending on the context, and sometimes the meaning can be totally different. In light of this, we believe that using BERT embeddings or ELMO instead of Word2Vec should yield more accurate results, given that BERT and ELMO consider the context itself. And that is why we decided to remove Word2Vec embedding layer and replace it with BERT or ELMO. And now I will leave you with my colleague Dina to continue.
So the first stage in our experiment was getting the training of the existing model to work and understand the technical details of it. After this, it was logical to explore the word embeddings of the data using BERT. So we implemented this using a pre-trained BERT model where tokenization and feature extraction took place. However, the output was dynamic. This means that if the question consisted of 8 words and the embedding dimension is 768, then the output of the BERT will be 8 by 768, where each word is encoded by a vector of 768 values. Now, if the question consisted of 5 words instead, the embedding will be 5 by 768. Now moving on, the next step was adding this to the BI-LSTM layer. However, this caused errors because we needed a fixed sentence representation for each question in order to be able to calculate the similarity between them. So the next stage was to have a model that produces fixed sentence encodings using BERT. By the end of the stage, each question in the dataset was represented by a vector of 1 by 768. Now the final stage, after exploring and understanding the embeddings, was to create a custom BERT embedding layer so that the rest of the layers can be built on top of it. We converted a pre-trained BERT model checkpoint into a trainable cross layer. Then we started progressing with building and training the model by integrating the rest of the layers earlier discussed to be able to calculate the And now I'll leave you with my colleague Ahmed Aboutaleb to walk you through our proposed architecture.
So, now that we have talked about the top 2 experiments, let's talk a little bit about the architecture that we are proposing. Our plan is to create a hybrid architecture that will utilize both BIO-BERT's ability to generate good embeddings for biomedical data and BI-LSTM's accuracy in question answering. The creation of this architecture will be our main mission for the second senior project. So, let me walk you throughout the architecture. Starting with the training phase, as you can see, the architecture is trained on question-answer pairs that are introduced as input and output. Using a pre-trained BIO-BERT model, the questions and the answers are converted into question embeddings and answer embeddings. These embeddings are later introduced to the BI-LSTM model to train it to predict answer embeddings based on question embeddings. Also, what is very important is to store the answers and their given embeddings in a lookup table that will be used later in deployment. During deployment, obviously, only the question is introduced as an input. Again, pre-trained BIO-BERT is used to generate embeddings for the given question. The now pre-trained BI-LSTM model is used to generate the embeddings for the answer. The embeddings generated is then used to look for the closest answer in the lookup table. So, we have managed to achieve the research goals that we have set for ourselves for this semester. First of all, we have found and gathered a lot of data. We also managed to figure out how to make these datasets compatible with the models that they will be used for. We also figure out the best text representation technique, and that is BIO-BERT. As mentioned earlier, we fine-tuned a model that already uses BERT with biomedical data, and it gave us better results, which shows that using a text representation technique that is based on biomedical data is definitely an edge. Finally, we introduced our own architecture that utilizes the main advantages in each of the architectures that we experimented with, and that is BIO-BERT's high performance in name entity recognition and relation extraction, and BI-LSTM's better performance in question answering. Given what we have done, we have definitely worked towards achieving our main capstone reinforcement outcome, and that's research. As mentioned in the previous slide, we have gathered a good combination of different techniques and datasets that, when hybridized, will create a new and promising architecture. The outcomes that are yet to be achieved are primarily the implementation of that new architecture and its deployment in case we have time and good results are achieved. Coming to the end of the presentation, let's talk about our plans for the second senior project. The very first milestone and the most demanding one would be to implement the architecture we proposed earlier. We'll also have to test that architecture and compare it to previous ones in order to make sure that we're moving in the right track. We'll then fine-tune the architecture to make sure that we'll get the best performance out of it. Also, what is very important is for us to expand the dataset. Therefore, we'll be constantly looking for more specific question-answer datasets to further train and fine-tune our model. We'll also try to expand the datasets through updating them periodically. The following are the list of references that were used throughout this presentation. Finally, we'd like to thank our advisors, Dr. Nouri Sakr, Dr. Ahmed Rafea, and Engineer Ayman, for their tremendous help throughout this semester. Thank you all for listening, and please let us know if you have any questions.